Good afternoon, everyone. My name is Noel Rappin from the RubyConf Programming Committee. I would like to introduce Aji Slater. Aji started their career as a vaudevillian, but in 2015 traded comedy bits for digital ones, performing with React and Rails instead of elephants. I have so many comments here, but I'm not even going to go there. Aji is co-host of the Tightly Coupled Book Club podcast, and according to this, is probably not Banksy. Please give a lovely RubyConf welcome to Aji Slater.
It's me. All right. It's been a long day. It's been a good day, but I know how these conferences can kind of take a toll. So if you're able and so inclined, I'd like you to stand up for a moment. And we're just gonna get a little stretch, get some blood flowing, get some endorphins going, like reaching up, going inside, going to side. But because we got limited space, how about you're diving into a pool, a little forward stretch, a little backward. Cool, thanks. All right. So yeah, thanks everybody for coming out. There's going to be code up here, so if that's important to you to read it, move on down. All right. Like Noel said, my name is Aji. I work at a place called ThoughtBot. And you may have learned, in the 1930s and 40s, there was a war involving many nations and peoples across the globe. So many, in fact, they called it a world war. It was the second of its kind. The particulars of the conflict are not what we're going to discuss today, but if you're interested in the period, I believe there have been a few movies, TV shows, even books where you can find out more. For our purposes today, all that's important is that you know that on opposing sides of the conflict were Germany and the United Kingdom. And at the time, long-distance communication was done in Morse code over radio and can be intercepted by an opponent in much the same way that we intercept the local top 40 station. The messages would need to be encrypted. The German solution for encryption was this, the Enigma machine. Not that much bigger than a typewriter, Enigma would encipher a given message before it was sent over the airwaves. The receiver of the message would also have an Enigma, and given the same settings that encoded the transmission, they could reconstruct the original message. The British solution for decrypting was this, Bletchley Park. Housed at this estate in Buckinghamshire was Britain's GC and CS, Government Code and Cipher School. The work was kept secret until the 1970s. Several thousand men and women, mostly college-aged, were tasked with cracking the German enciphering system. And if you know of Bletchley, the story you've likely heard is his, Alan Turing, of the Turing test, Turing machines, Turing patterns. Maybe you know the negative proof of the Entscheidungsprobleme. Or maybe you've just seen him on the 50-pound note. Building on the work of Polish codebreaker Marian Rejewski and his precursor machine called Bomba, Turing realized that a quirk of Enigma's wiring could be exploited and designed a special-purpose computational engine that was made real by the engineering brilliance of Harold Keen and the British Tabulating Machine Company. After incorporating a crucial insight by English mathematician Gordon Welshman, Bletchley's secret weapon was christened Bomb. On 108 cacophonous rotating drums, it could crunch through 17,576 possible Enigma settings in just 20 minutes. And depending on who you ask, the work at Bletchley shortened the war by 2 to 4 years. If you're interested in hearing more about what it was like to be a part of Bletchley's operation, I would really recommend The Secret Lives of Code Breakers by Sinclair McKay. The Enigma was operated by German communications agents working in pairs. One to operate the keyboard, entering the message. As a key was pressed, the corresponding letter would light up on a lamp board and be written down by the second. It worked like this. It's a simple electronic circuit, and if you're unfamiliar with that sort of thing, you can think of the wire as a tube that carries electricity. When the switch is down, the signal flows, and when that signal touches a light, it will illuminate. Now, imagine that there are more of these simple circuits, 26 of them. A to A, B to B, C to C, on down the alphabet. And if the connections between the key and light are changed, well, then the signal would be encoded. Press the A key and B lights up. If you knew which letters were connected, you'd be able to decode it as well. That's the job of Enigma's encryption mechanism. It physically swaps the electrical connection between the key and the light. Maybe you've made a code like this before. When one letter is replaced by another like this, it's known as a substitution cipher. But no matter how much the key is scrambled, substitution ciphers are trivial to break. So Enigma was more. The heart of Enigma's encryption engine are several rotors, shown here with the left and right sides. Each had 26 electrical contacts on those sides and could be turned to set the machine at any one of those positions. Internally, a wire goes from a contact on one side to a different contact on the other. So the signal might come into index 0 on the right side and be wired to index 8 on the left, then 2 to 21, 3 to 14, and so on. But if it remained as simple as a substitution cipher, it would be just as easy to decode. So Enigma accepted 3 rotors, each with different internal connections. And there weren't only 3 rotors, but a set of 5 to choose from. And those 5 could be entered in any order for 60 possible combinations. When mounted on the internal spindle, the rotor's 26 connection points lined up, and a signal would be sent through them, coming in from the keyboard and be switched to different indexes by each rotor in turn. After the 3 rotors came a spectral symmetric rotor called a reflector. Here, if 1 becomes 10, 10 becomes 1, and after passing through the reflector, the signal would be carried back on a different path of connections. This is how Enigma both encrypted and decrypted. Because the path of the signal is symmetrical, typing the cipher character will return the original. But no matter how many times a letter is changed, it's weak if A always becomes E. So the rotors rotated after each character, the signal taking a new path through, meaning the same key pressed twice in a row would yield 2 different encoded letters. Techniques that make a substitution cipher easy to break rely on repetition, statistical analysis, and they are useless against this. A key that changes not once a day, not once a message, but once per keystroke. And they didn't all rotate at the same speed. The second wheel wouldn't advance until the first one made a full revolution, and so on. That means Enigma is a polyalphabetic cipher with a new key every letter based on the starting settings of the machine. Each rotor had 26 positions, 3 rotors, makes 17,576 possible starting positions. In 60 rotor combinations, means 1,054,560 possible settings permutations. But the German military Enigmas had another layer of encryption that commercial versions did not. At the front of each device was a plug board with a connection for each letter. Up to 10 combinations could be made with short cables. Cables that would change the signal's value between the keyboard and the rotor mechanism, effectively making small, arbitrary changes to the cipher's key. In order for German military to all be speaking the same cipher, a chart would be sent out from high command prescribing which setting should be used on a given day. This was an essential communication because only by sharing the same starting settings would agents be able to communicate. The chart included which of the 5 rotors to use and in which order, the starting positions of the rotors, and the 10 pairs of plugboard connections. Combining all of these options takes the possible settings to an astronomical 150 million. Portable electromechanical encryption equivalent to a 67-bit encryption key. Enigma has a practical link to early computing history, and because of the events of its time, we can directly connect Enigma and Bletchley to what we do and why we're here. It's a remarkable object, and that's a key word today, object, because Enigma will be our platform to explore principles of object-oriented programming, OOP. OOP. A strength of which is said to be how it models the real world, but objects in the real world are very different than objects in a code base. Enigma, on the other hand, it's a physical device. It has moving parts, actual objects that each perform a part of the larger whole by sending messages along a wire to other objects. If the image we're supposed to have of OOP is objects sending messages, then Enigma might as well be its mascot. We can recreate this mechanism in code without abstracting our conception of an object beyond recognition, because we could literally hold in our hands the pieces of an encryption algorithm. So let's go big right from the start. 2 truths of software development. Requirements will change. And this is good. If nothing needed to change, you probably don't have any users, and we'll need to find a new job. And we will never know less than we do right now, because we don't know how things are going to change. And it's frustrating when we can't make changes, right? When a new feature request comes along and we can't deliver it to users because it would be too hard to implement. That's an awful feeling. I don't want to be there. But if we don't know anything and it's all going to change, how can we build anything at all? Object-oriented design is one strategy to do just that. OO design is about making change easier by managing dependencies. So what principles are we going to explore? The single responsibility principle. We'll gather together the things that change for the same reasons and separate those that change for different reasons. Abstraction. We'll manage the complexity of implementation by substituting a more easy to reason about representation. Encapsulation. Object's internal data should change on that object's own terms. Dependency inversion. Conventional architecture would have utility modules at a low level consumed by higher level ones, but we'll invert this thinking and increase reuse from top to bottom through interfaces. And the open-closed principle. An object should allow its behavior to be extended without modifying its own code. All of this in service of small, simple objects sending messages. So let's start up the slide deck text editor with a new file, enigma_test.rb. We're going to use an abridged test-driven development technique today because we Rubyists love tests, right? We know this because there is a test framework in the standard library. A mini-test test suite is made up of Ruby classes and methods. Tests we write will be defined inside a class that inherits from mini-test test, and we can get things moving by thinking at a high level. What does our Enigma need to do? Encipher a character, right? Mini-test is not a DSL. Tests are methods in our class whose names start with the word test. We'll initialize an instance of our Enigma class and call a cipher method, asserting that it returns a string, and that string is not the one that we started with. All right, that looks like a thing. Let's make that happen. With a class and a method called cipher. We'll invoke the test file from the command line. By requiring mini-test auto-run like we have, mini-test will find all the runnable subclasses and tell them to do their thing, which right now is to fail. There isn't any code yet, so if that had passed, we would know that that's probably a bad test. Let's add another before we move on. It should encipher into a different letter for each character. We can make sure that it's not A and that ciphering B isn't the same result. Is this test going to pass? No, of course not. Add an alphabet constant and a substitution key with the order of real World War II Enigma rotors, by the way. We'll make use of the rotor being an array, get the index of the message character from the alphabet, then through that a letter from the rotor. And we'll do it 3 times. Show us the tests. Nailed it. I always say, did it work? Commit. We add initial Enigma class with cipher method. We made use of test-driven development flow and set up initial Enigma file and functionality. The person in the front row over here really liked it. They were nodding a lot. If you need a primer on writing useful commit messages, I hear this talk is pretty good. Tests are green, so let's refactor. Red, green, refactor, but this is not a talk about TDD. This is, though. You should watch that later. We've all heard of dry, don't repeat yourself. So what stands out? For sure. But to make sure that we're on the right track, we should ask ourselves, are these lines going to change for the same reason? Are they doing the same thing? Do they have the same responsibility? In this case, absolutely. They're responsible for how we convert a character into its matching integer. So we gather together things that change for the same reason to create a single source of truth. Replace all of the alphabet.index calls with our new method, and radio for backup. Situation green, 10-4, good buddy, over and out. Is there another method to extract here? What about this one? This is responsible for how we change that integer back into a letter. By introducing a translate method, we create the source of truth for using the rotors. If that needs to change, we can change it in 1 place and not 3. And look, we can use the alpha index method we just made and remove a lot of noise. Now the real test, the tests. Still good, all right. Did it work? Commit. We extracted alpha index and translate to private methods. We gathered lines that would change for the same reason, guided by the single responsibility principle to create a single source of truth for those behaviors. One benefit from extracting methods is that we get to name things. Then what the Enigma class is really up to is easier to see. We can see that it's translating, it's ciphering, that's what we expect the Enigma to do, but it's also handling input. So Enigma converts letters to numbers and uses those numbers to get a new string. Words like and, or, also used in describing our class can be a sign that it's doing too much. So let's create a new collaborator where indexing is its purpose. If we think of the actual Enigma, maybe that's the keyboard. So brand new files, tests all set with imports, class declaration. Test that it converts a letter to an alpha index. That's behavior that we're trying to move to the keyboard class. Some simple assertions, do the letters change the way that we would expect? We'll take advantage of the existing behavior. Simple green, back to Enigma. So we'll add the keyboard class that we just made. We'll get rid of the alpha index method, and now translate uses the keyboard instead. And we're at a point where all of the pieces should fit together again, but do our tests agree? Oh, and we also have more than one test file now, so we'll use a little Ruby command line magic to run every file that ends in _test.rb. Magnificent. There's something wrong with this Enigma, though. Because we're converting alpha to int and back between each rotor, we're not correctly following the connections through our device. So how do we correct this? We use integers the entire way through. Convert only up front and at the end. This is going to remove a lot of overhead. Where we use the keyboard is going to move to convert just once and stay an integer until the end. What do the tests say? Kermit was wrong. It is so easy being green. We need a lamp board too, come to think of it. So that's the other side of the keyboard. It's the keyboard, but in reverse. It's not alphabet.index get integer. It's start with an integer, get back to the letter. Same way, it's a drop-in replacement to our Enigma class. Ooh, greener than Al Gore on Arbor Day. Okay, let's try something. I'll say, did it work? And you'll say, commit. Okay? Did it work? Commit! Nice. Some of you were paying attention. Some of you weren't. It's okay, I'll get over it. Eventually. Try it again. Did it work? Commit! All right. I'm not the only person that thinks this looks like a young Patton Oswalt, am I? Okay, this commit extracts alpha and int translation to classes of their own. Before this, Enigma methods contained the code that implemented the behavior, preventing flexibility and reuse. We extracted self-contained functionality, replacing the specific code with a message sent to new collaborators. And this abstraction makes Enigma lighter, easier to understand, and opens it to new functionality. The smaller classes offer utility and reuse to other parts of a larger system. So let's write some more tests. We're going to test that it enciphers according to the settings. So Enigma's settings would be changed by the operator, so we'll add that function. That does mean that we'll need some rotors to test with, that's all right. And let's say that starting settings means .new. We know the rotor position, so we will assert on the precise result that we expect. And a failure is the precise result expected here. We have written no new code. All right, fold that up and pass in the rotors just like the test says. Now we can move on to changing cipher because the rotors aren't created here anymore. And the way that the way to translate needs to get an update as well. So we've begun replacing the literal references to arrays with an abstraction that allows this class to be much less involved in the implementation. Green like Donatello. The Ninja Turtle, not the sculptor. Let's look at translate again. Some of you need to bone up on your Renaissance sculptors. And there is an object hiding in this class. And it's not even hiding very well. Because what is an object? It's a combination of data and behavior. Here's the data. Here's the behavior. And besides, look at this method. It's a method that just calls another method by smushing together its arguments. Keyboard and integer arrays have made this obsolete. Let's not let that object stay hidden. It deserves a day in the sun, and Enigma doesn't need the extra implementation anyway. So we'll test that it translates based on its key, which in the real one is a little mess of wires between the right and left sides of the rotor. Here, the key is an array, and the argument to .new. We'll use a simplified key rather than the whole Enigma set because this is enough to have a good test here. Don't overcomplicate it, it's only going one step. But the test is still going to error, and we expected that. This is pre-recorded after all. And we have the wrong number of arguments to .new. Starting settings means initialize. We'll carry that forward throughout this process, and translate means brackets. We know that from before. Oh, emerald green. But Enigma is still using the old way, so let's use the new rotor class instead. The good news is that the rotor arrays are already arguments, but we'll instantiate and pass in rotor instances instead. Errors, errors, errors. Instead of Enigma sending a message to itself, we have collaborators, small, simple objects sending messages. Enigma sends the message to each rotor in turn. Each message sent to a rotor is 1, 2, 3. See that here? 1, 2, 3. Translate method. Bye, Felicia. Back to the whole thing being able to fit on the screen at once, too. Oh, you just love to see it, don't you? Did it work? Thank you. This commit extracts rotor class. The things that don't align to Enigma's purpose are in their own classes, and we're left with a clear picture of what the Enigma class does. It orchestrates and conducts the communication between these different pieces so that they can stay separate from each other. A rotor doesn't have to know what comes before or after it, and Enigma doesn't know how the work gets done. That's dependency inversion at work. Okay, let's get fancy. We're going to test that it enciphers a phrase correctly. No longer single character strings to the command line. Sounds about right. Let's get rid of that red. No changes to initialize, though. We're going to split the string into single characters and smush them back together at the end. It already does one character, so we'll call up our friend.map, do that for all of the characters, and that should work, right? And the tests agree. So let's go. We're still missing some key functionality, a lot kind of. As it is, even with the phrase, it's still just a substitution cipher, right? And we can't have that. Test that no repeats in consecutive ciphers. So if we cipher A, then cipher A again, it should not be the same result twice in a row. And that shouldn't only work for 2 calls to cipher, but in a phrase too. Show me red, 2 failures. If Enigma is our coordinator, rotor position doesn't really seem to fit there. How about the rotors? We want to know that the rotor can step 1 position, but also that it's not going to fall off the end of the key. So with the minimum amount of setup needed to test this specific case, and here we advance. We should prefer that our tests be straightforward. Coming along and reading this test later when we've forgotten what we wrote shouldn't take a lot of energy. Mini-test, do you have anything to say? Gross. Position is data internal to the rotor. No accessor methods to be modified directly from the outside, not even any public API revealing that there is an instance variable. Now, position is part of how we calculate what index to return, and it passes the first test. Okay, this is neat. Down here, Ruby has a method that moves the first index in an array to the back with an argument for how many times to rotate. Also, notice, does anybody else get to see this method? No, it is private. That's encapsulation. So how did we do? Rotor is good, okay? Enigma's gonna have to wait for another moment though. Because remember the daily settings? Position needs to be configurable. Settings equals initialize, we set that up before. So let's give it a default value. That way we don't have to update every rotor.new in the code base. And after a full rotation, it needs to let the next rotor in line tick over. We'll return a Boolean when advance causes a position to make a full rotation. And by not specifying a method tied to how and when, we leave flexibility for future rotors to decide differently, and to do it without changing a line of code outside of the rotor. Because by the end of the war, there were machines that had rotors with 2 places that would tick over, or some Enigmas had 4 rotors. So let's keep that flexibility. And let's set it back to 0 so we're not key.rotating 100 times. All right, the rotor tests pass, and we have what we need to make the Enigma tests function. So back we go. Like St. Andrews, we are on the green, and that is a golf reference. I apologize. Let's refactor. There we go. We can make it a little more comfortable in here by extracting some methods. We'll search for things that change for similar reasons. Those lines enciphered a character. Well, that sounds like a method name, encipher character. What do these do? Well, they advance rotors. Naming things isn't hard. Naming these things wasn't hard. And we encapsulate Enigma's internal mechanisms as well by making these methods private. They weren't callable from outside the class when they weren't methods, so they shouldn't be now. Future coders will know that these are not meant for reuse and aren't tested in isolation. These messages are internal memo only. So how did we hold up? Yes, fair degree. Fair degree is the green patina on copper, like the Statue of Liberty. This is getting away from me. But, did it work?
Commit!
I can't hear you.
Commit!
This is fun, you gotta try this sometime. So this commit implements rotor stepping behavior. With new behavior, Enigma is no longer a weak substitution cipher. We safeguarded the rotor's internal data, only allowing it to change via a method without exposing how the behavior is accomplished. We're encapsulating this information. We're also protecting rotor's collaborators from the responsibility of knowing that this is what rotors do. Now, when I think about the Enigma machine, it's made up of 3 different high-level parts working together, like the keyboard, the lamp board, and the enciphering mechanism. The core of that is the rotors, but there's more to it. There's the mechanism that advances the rotor. There's the reflector. There's the spindle that the rotors sit on. So we'll need a new, small, simple object to send messages to. We'll call it a spindle. Instead of passing rotors to Enigma, we'll pass rotors into the spindle and the spindle to Enigma. This test causes the first rotor to complete a full turn, and we're asserting the second rotor got the signal. Yeah, it was never going to work. Navy Enigmas use 4 rotors at a time. Army and Air Force used 3. If it's not hard-coded, ours will have that same flexibility. Look familiar? That's the body of the .map from the Enigma class. So we don't know how many rotors. We'll iterate with my favorite enumerable method, reduce. Have you been introduced to reduce? Reduce iterates the array. Each iteration gives us the current object and the return value of the previous iteration. But the first iteration gets the argument. It's the same game in advanced rotor, except that if the step signal is true, the rotor advances and sends its step signal down the line. We start with true so that first rotor always advances. And if the rotor .advance returns true, step signal will be true for the next rotor in sequence. Also, please don't use a ternary here unless you are also running out of room on your slides. Oh, we are so green we get mistaken for the Incredible Hulk. Ooh, got me. See, I was using that as a rhetorical device to summarize when we finished the topic, so hang on. Back in Enigma, the rotors are not Enigma's responsibility anymore, which means that this isn't either. We've got breathing room to open cipher. We're abstracting so well, we're abstracting away what class it is. No depending on any class whatsoever. We're only responsible for the idea of what this class is, a transformer. If someone wants to use this class, they don't even have to use a spindle. The modules are loosely coupled and whole new functionality doesn't need to change code in this file. We know less now than we ever will, but because of OO design, it doesn't even matter. Just pass in a different transformer. You want to use elliptic curve cryptography? Go right ahead. You want to use MD5? 1993 called and they want their algorithm back, but you can. I'm excited. Are you excited? Green, green, green. Green like, I don't know, all the little dots in the terminal. I'll be with you in a second. Hit me, baby, one more time. Did it work? Thank you. This commit abstracts everything away from Enigma's responsibility. Enigma is open for extension and closed for modification, enabling painless reuse in ways that we don't even have to try and predict. Led by OO design principles, we built an Enigma replica that is easy and fun to work with. using tech and ideas that stand on the shoulders of giants like Alan Turing, John von Neumann, Grace Hopper, and Yukihiro Matsumoto. What a ride. Single responsibility. Objects and methods that strive for a cohesive, unified purpose. Abstraction. Relocating implementation, replacing it with a simpler to reason about representation. Encapsulation. An object should respond, react, and update on its own terms. Dependency inversion. Higher level objects operate without being involved in the specifics of those that they send messages to. Open for extension and close for modification because you don't even need to. All in service of small, simple objects sending messages. Because change is hard. And it doesn't have to be. Thank you all so much. This is fun. We should do this again sometime. If you want to chat more about features to implement with Enigma, we didn't even get to the reflector or the plug board or a lamp board that could return HTML instead of a string, or a keyboard that's actually an API endpoint, or maybe you too have feelings about how Turing was murdered by his own government, or maybe you want to chat about Bletchley Park or like object orientation. I'm going to be hanging around the Thoughtbot booth a lot tomorrow, so come by and say hi. Thanks again.